Hello, this begins the second video that supports the math notes for, again, this is Chapter 8 of Integrated Math 3 for CPM, where we are learning to look at graphs as well as look at factored form equations of polynomials to be able to move back and forth in between writing an equation given a graph or, given a graph, write the polynomial equation. So we use clues as x-intercepts are the best clues to be able to write the equation. And so here, looking at this graph, I see that I've got an x-intercept at x equals 1. I see another one at x equals 1, 2, 3, 4. And finally also at 1, 2, 3, negative 3. So x equals negative 3. A couple of things to notice right now is that this particular example that I'm going through right now is actually an example of an odd degree polynomial. So notice again, odd degree polynomials, they start and end in different directions. I also know something about the stretch factor of this because it starts in, again, this quadrant down here, and then it finishes up over here. This a value is going to be positive. So I already know that a value is going to be greater than 0 before I even solve for it, based on the fact that, again, it starts there and finishes up here. And again, now I have to put all of this together to write the equation. Notice there are no bounces and there's no flattening. And so all of these roots here are going to just be single linear factors. They're not repeated because, again, they just pass right through the axis. So starting with writing the equation, I can start with y equals, and again I use each one of these x-intercepts that I've identified. First, the unknown stretch factor, x plus 3, and then we're going to have times x minus 1 times x minus 4. So again, I'm using this whole idea of zero product property working backwards from the x-intercepts to figure out the linear factors. But since we know, and they told us that it passes through 0, 12, so again, this point right here, they're saying is 0, 12, I can algebraically solve for a by substituting in that value. So when does 12 equal a times, and again, if I substitute in 0 for the x, that really just changes this to 3, negative 1, and negative 4. Multiplying these together, I actually get 12 equals a times 12. So here the a value is just 1. There is no stretch to this particular graph, but I did confirm again that I wrote the equation correctly because I didn't get a negative or anything like that. So my final equation here would just be y equals x plus 3, x minus 1, and x minus 4. And so again, this is a great time for us to, again, think about what is the degree of the polynomial in factored form. It would be a third degree polynomial because if you multiplied all of this through, eventually you would have an x cubed term. Let's go through the next couple of graphs as well. So I'm going to move down to another example that's in the category of even graphs. Again, this is an even function. One reason I know from looking at the graph that it is even is that it starts and ends in the same direction. So I already know that it's even. But because it opens down, right? This opens down. That actually is a little reminder to me that I know that my a value, a will be negative. So I can algebraically solve for this to confirm that as well. So let's again label where are our x-intercepts. It looks like we've got one of them here at negative 5, the other one at negative 2, the next one at 3, and then they have that one at 5. So putting each one of these together, now I've got y equals, and again, each one of these passes right through the x-axis. It does not flatten, so there is no cubed linear factor. And again, there's no bouncing. It just passes right on through. That means each one of those linear factors is just going to be a single linear factor. So x minus a negative 5 turns it into x plus 5. Then we have x minus a negative 2, x plus 2. Then we have x minus 3 and x minus the 5. So again, this right here matches this graph. And now since they told me that the y-intercept occurs at 0, negative 15, I can plug that in to my equation to algebraically solve for the the stretch factor. So I apologize that the lighting is a little bit off. It's almost sunset. So let's see, negative 15 equals a times, and again, we're just substituting in 0 for the x, so really I can think about all of those x's go away. And then we've got negative 3 and then negative 5 here. So simplifying this, I'm actually going to continue my work down below. We've got a times, and then 5 times 2 is going to be 10. And then we've got the 10 times, again right here, this is a positive 15, so that's actually 150. And now if I take and divide both sides by 150 and I divide this side by 150 to solve for a, I actually get that the a value here is negative 1/10. So it's a very small value, but notice it is that negative that I anticipated based on this being a 4th degree polynomial opening down. So my final equation is y equals negative 1/10 x plus 5, x plus 2, x minus 3, and x minus 5. And so again, that will be the final equation that I will also think about, that if I multiplied that out into a standard form, I would have an x to the 4th term. And so that is telling me that, yes, it's a 4th degree polynomial. And again, it is going to open down. The very last problem that I had in the notes was to start from an equation and then to sketch the graph. And so one of the things that we've been working on, starting from the previous lesson, is the idea of what happens when we have repeated roots. And so this equation here, I said, given the equation, sketch the graph of the polynomial. So I need to use this factored form really to inform me almost like clues. That I can see that, first of all, the a value is negative, right? So a equals negative 1. That tells me something. Also, I need to think about, oh, well, right here, we've got this squared linear factor. So anytime we have a squared linear factor, that implies that it will bounce off of the x-axis at that point. So it will bounce at, and the x value, in this case, that would make that 0, is an x value of negative 2. Looking at the next linear factor right here, notice it's cubed. So this is a cubed linear factor, and so I was going to write down that a cubed linear factor, what actually happens is that it flattens when it passes through the x-axis. So it flattens on the x-axis at the x value that corresponds to that x-intercept, and that would be at x equals negative 1. Now, before I generate my curve, again, I'm thinking about all of these clues. The last clue is to think about, well, what is the order of the polynomial? Again, the degree of the polynomial, or the highest ordered term, that would end up being an x squared term here and an x cubed term here. This is an x to the 5th polynomial, right? So this is a 5th degree polynomial, and that's odd. And so thinking about it, remember, it will start and end in different directions, right? But because of the fact that that is a negative 1, it will not look like this, because this is for a greater than 0. So this should look like this, right? When a is less than 0, because again, it will start and end in different directions. I can work with, again, now my x-intercepts to figure out exactly how many humps are there on this particular 5th degree polynomial. And so now let me go ahead and plot some of these points on an axis system. Again, I would have a negative 2, I would have a 0. Also, it looks like this should have been a positive 1. I apologize, I made that mistake, but I can see that now as I double check that my correct x-intercept here should have been 1, and so here I've got 1. Now, of course, I should generate a y-axis as well to show that this is the y-axis, and here is the x-axis. Now, each one of those x-intercepts, the negative 2 and the 1, I will actually put on the graph here. If I think about my y-intercept, that would be a helpful thing to know as well. So the y-intercept is, again, a reminder when x equals 0. And so if I substitute in 0 there, I get this negative, right? And then I've got 2 squared, and then I've also got negative 1 cubed. Again, when I substitute in 0, I don't really have to write that. That's pretty much implied. But that negative, or anytime there is a stretch factor, will impact that y-intercept. So make sure to not drop that. And so finally, multiplying that through, this would end up being y equals negative, right? And then we would have 4 here, because 2 squared is 4. And then the negative 1, when you cube it, it actually stays negative too, right? Because it's negative 1 times another negative 1. And so now altogether, I have got a y value of positive 4. And so I don't have to totally scale this correctly. I'll just pretend that this is, again, 4 right here, and that's my y-intercept. Now I use this concept of the fact that it is going to start up here and end over here, right? So again, I'm going to start in this quadrant. This is the third quadrant, and I'm going to end over here because of the fact that it's negative. I also need to take into account that it's going to bounce off at negative 2. And remember, it's going to flatten through when it passes at 1. So here goes. We start up in this region and we come down and we bounce off the x-axis before coming back up, passing through that y-intercept. Before it comes back down, and as it approaches the 1, it comes down and it flattens, and then it comes back out of the x-axis. So again, right here, there's the bounce. And that bounce happens again at negative 2. And notice right there, there is a flattening of the curve. And that flattening happens because of the fact of the cubed linear factor. Before I conclude, the other thing to do is to always check that it makes sense. Looking back to the original function, again, it was negative. So again, in this case, it was going to start up high and finish down low if we're thinking about reading from left to right. We've got our x-intercepts at negative 2 and at positive 1, which make each one of the linear factors 0, the concept of zero product property. And again, the squared linear factor here indicates that there will be a bounce at the negative 2. And again, at the cubed linear factor here indicates that we would have a flattening of the graph. And so all of those things match my expectations.